So we've talked a lot about different gas laws. Remember, a law says what happens. It just describes what happens. It does allow us to predict the future, but doesn't explain. So here's the theory about gases. It's called kinetic molecular theory. It's based on the movement of molecules. It's the simplest model, and it works pretty good. Pretty well, I should say, proper English, right? So we model a gas as a collection of particles. So these could be molecules or atoms, and they are in constant motion. And so the idea here is that the particles are going to move in a straight line until they run into something. Because they're not going through air, they are the air, right? They are going through nothing. So there's nothing for them to run into until they happen to hit the wall, like here's one's colliding with a wall, or they can collide with another gas molecule. When they collide with another gas molecule, they bounce off of each other. They don't interact at all. They just bounce off and keep going. So one of the important things about this theory is that the size of the gas particle is negligible. Now we know that they do have volumes, but they're so small they don't matter. It's like talking about the volume of people in the state of Wyoming, right? Compared to the size of the state, the volume of the people just doesn't matter at all. And that's the way it is with gases. There's just so much empty space. As an example, at STP, the argon atoms only occupy 0.01% of the volume of the gas. That's pretty small. If the argon atom was the size of a golf ball, its nearest neighbor would be 4 feet away. And in between would be absolutely nothing. Not air, nothing. So there's lots of space. The average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. Temperature is a measure of average kinetic energy. Higher temperature, higher average kinetic energy. Now it's the average, right? So some of them are moving faster and some are moving slower. The temperature measures the average. Collisions, when a particle collides with another particle or with the walls, it's a completely elastic collision. So this is physics. When the two particles collide, they can exchange energy, but they don't lose kinetic energy. So these are like billiard balls bouncing off of each other. These are not like balls of clay. You imagine two balls of clay colliding with each other, they go funk and they just stop, right? Whereas really hard billiard balls, you hit one into the other and that one goes shooting off. Aside from the rolling part, there's no loss of kinetic energy. Elastic collisions. So the energy does not get lost when they collide. So the gas particles have this average kinetic energy and they just keep going. They don't slow down and stop because there's nothing that causes them to lose kinetic energy. They're just bouncing into each other. It's like a game of I forgot the name of it. It was Pong. It was Pong, right? The original video game. So here we have, this is an elastic collision. So two billiard balls, they came from up here. They come here and they run into each other and they bounce off of each other and they keep going. Two lumps of clay rolling into each other go funk and stop. The kinetic energy that they had gets dissipated as heat when they run into each other. They've lost their kinetic energy. Gas particles do not do that. So we can use kinetic molecular theory to explain gas pressures. So the particles are constantly moving, they strike the container, and they have a force, right? So many particles hitting the walls are going to add up to a pressure. So pressure is the force. Each particle exerts a force over an area. We can explain Boyle's law. The volume of a gas is inversely proportional to the pressure. If we decrease the volume, that forces the molecules into a smaller space, right? If we're keeping the temperature and the number of particles the same, we've got those particles in a smaller space, they're going to run into the walls more frequently. That means the pressure is going to go up. So as the volume goes down, the pressure goes up. That's what Boyle's law tells us. Charles' law says the volume of a gas is directly proportional to the absolute temperature. So when we increase the temperature of a gas, we increase the average speed, we increase the average kinetic energy of the particles. In Charles' law, the pressure needs to be held constant. And so that's done by allowing the gas to change its volume. So if we've got the gas particles moving faster, they're hitting more frequently and they're hitting harder. In order to keep the pressure constant, because that would cause an increase in pressure, we have to increase the volume and spread the collisions out over a larger area. Avogadro's law tells us that the volume of a gas is directly proportional to the number of gas molecules. We can explain this with kinetic molecular theory. If we increase the number of gas molecules, then there's going to be more in that container. They're going to hit the walls more frequently, right? Again, with this law, we're keeping the pressure constant. To keep the pressure from going up, we have to expand the volume to spread it out over a larger area. Dalton's law of partial pressures. Total pressure of a gas mixture is the sum of the partial pressures. Well, kinetic molecular theory tells us that the particles have negligible size and they don't interact with each other. So we've got particles of different masses, but they have the same average kinetic energy because that's what the temperature is. It's the average kinetic energy. So if you have a small gas particle, it's going to have a higher speed to have the same kinetic energy as a large gas molecule. But the average kinetic energy is the same. So the pressure from the different kinds of gases is going to be the same. So each of the gases just exerts its own pressure, and that adds up to the total pressure. Kinetic molecular theory predicts behavior that's consistent with our observations and measurements of gases. The scientific theory is the most powerful kind of scientific knowledge. This model does break down under certain conditions, but by looking at where it breaks down, it helps us to understand even more about the gases. So even though this theory is not perfect, looking at its flaws can help us understand even more. So the average kinetic energy of the gas molecules is going to depend on the mass and the velocity. So kinetic energy is 1/2 mass velocity squared. So average kinetic energy will be 1/2 the number of particles times the mass and the root mean square velocity. So in order for these to have the same kinetic energy, they're not going to have, if they don't have the same masses, they're not going to have the same velocities, but they can still have the same average kinetic energy. So instead of velocity, we use U. It's the root mean square velocity. It's a special kind of average. That's as much as you want to know about that. It's a special kind of average. So it's close to a regular average velocity, but it's not exactly. So in a gas mixture at a given temperature, lighter particles travel faster than heavier ones, right? Because, let's do this. Kinetic energy is 1/2 mv squared. If the mass is small, the velocity has to be higher to have the same kinetic energy. If the mass is large, the velocity will be smaller. So Football applies to many aspects of life, and it makes a great analogy for gas molecules. So you've got the running backs. Those are the smaller guys, and they're really fast, right? And then you've got the linemen, and they're really big. Are they faster or slower than the running backs? They're slower, because really big guys move slower than small guys, right? So the small particles move faster, the big particles move slower. Same kinetic energy, though. Okay.
Like, what if the smaller particles have a higher?
The smaller particles do not have a higher kinetic energy. They're moving faster, but their mass is smaller. So small mass times higher velocity, or large mass, slower velocity.
So,
Okay? Yeah. So the velocity of the particles is related to their mass. So the average kinetic energy comes from the temperature. So how do we know how fast or slow these guys are going? Well, we can use this equation. The root mean square velocity, or the average velocity of that kind of particle, is the square root of 3RT over m. Here, m is the molar mass in kilograms per mole, not grams per mole. And we're going to use a different kind of R. It's just got different units. 8.314 joules per mole Kelvin. It's the same quantity as 0.08206 liter atmospheres per mole Kelvin, but it's got a different unit. It's like measuring a piece of wood that's 2 feet long. I'm saying it's 2 feet long, and you're saying, no, it isn't. It's 24 inches long. Well, it is 2 feet, and it's 24 inches, right? Just different units. That's all this is. It's R, the ideal gas constant, with different units. So 3RT over the molar mass in kilograms per mole. The reason we need kilograms here is because that's going to work out with the units of joules. I would give you this equation, and I'll give you this R on an exam. So let's calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So we need that equation that we just looked at. So the root mean square velocity is equal to 3RT over m oops, good grief, there's too many bumps in my m, where this is the molar mass in kilograms per moles. So we've got 3RT. This is our temperature. For R, we're going to use the units joules per mole Kelvin. What unit do I need for that temperature? Kelvin. So 25 degrees Celsius, I need to put that in Kelvin. And the molar mass, kilograms per mole. Xenon, right? Xenon 131.3 grams per mole. I need to convert that to kilograms. So if I want kilograms on the top and grams on the bottom, kilo means 10 to the third. So I'm dividing. It's going to be 0.1313 kilograms per mole. So I've got R, I've got T, I've got molar mass in kilograms per mole. And plug them into this equation. So we've got 3 times 8.314 joules per mole Kelvin. And I've got the temperature, 298 Kelvin, and I'm dividing by 0.1313 kilograms per mole, and the square root of the whole mess. So let's look and see what happens with the units. I've got Kelvin canceling Kelvin and moles canceling moles. What I'm left with there is joules divided by kilograms. A joule is a Newton meter. Yeah. So a joule is a Newton times a meter. A Newton is a kilogram meters per second squared. And so, I know, right? It's a mess. I'm not expecting you to do this, but I want to show it to you once. So you can say, oh yeah, she showed me, it works out, right? So joules per kilogram. So I've got Newton, so I've got kilogram meters per second squared times meters divided by kilogram. So that ends up being, the kilograms cancel out, that ends up being meters squared per second squared. So the unit here inside of the square root is meters squared per second squared. When I take the square root of that, I get the unit meters per second, which is velocity. So I do the math. On my calculator, I do the square root symbol first. You need to figure out what your calculator wants you to do. And I've got 3 times 8.314 times 298 divided by 0.1313 equals 3 sig figs, 237.92, which would round to 238 meters per second. Are these atoms moving slowly or quickly? 238 meters in a second. That's pretty fast. Any questions? I'll take that as a no. Completely clear. Yeah, question?
You're going to give us the constants?
Yeah, I would give you this constant, and I'd give you this equation. We don't use it very often. What's important is that you know how to use it. Okay, so there's a relationship between molar mass and velocity. Here we've got a graph showing relative number of molecules with the indicated velocity as a function of the velocity in meters per second. So if we look at these different gases, oxygen, nitrogen, water, helium, and hydrogen. Hydrogen is the smallest, it has the lowest mass, and oxygen of these has the highest mass. What we see is not only does the peak where most of the atoms are, or the molecules are, not only does this move out towards higher and higher velocities for the smaller atoms or molecules, but we also see a change in the shape. So the oxygen has a fairly steep peak here compared to the hydrogen, which is very spread out. So the lighter particles have a broader distribution. They have a wider range of velocities. So you've got some that are really slow, some that are really, really fast compared to the average. Whereas for oxygen, the range of velocities is narrower. As the temperature of a gas increases, its average velocity is going to increase. So here, similar kind of graph, just with a single type of gas, looking at different temperatures. 273, so that's 0 Celsius. Here's 1,000, here's 2,000 Kelvin. And so as the average velocity increases, again, we see the distribution broaden. So when the average velocity is higher, there's a bigger range of different speeds.